So, if you're involved in the math community, you should know what the MIT integration bee is. The MIT integration bee, it's one of the most hardest integration bees in the nation, and I think around 20 to 30 students partake in it, going from the going from the prelims to the finals. And what if I told you that these integrals are actually not very hard at all? And I think it's so easy that I could teach this starting from what you learn at the beginning of calculus, the derivative, all the way up to this MIT integration bee or integral, which was actually in the finals this year. So let's get to it. What is a derivative? Huh? I think let's start with that question. Well, a derivative is the slope, the instantaneous slope, which means that it's the slope at a point. So essentially, it's a tangent. So say I graph this function f of x, right? And I graph this point right here. The derivative of this function at this point would just be the tangent. So let me just draw this in. This is essentially what a derivative is, okay? So, how do we derive this? So let's say we have 2 points, okay? And we want to find the secant of this, okay? We want to find that. Well, that's just our slope formula, and we all know what the slope formula is, right? We know that it is y2 minus y1 all over x2 minus x1, right? So, we can say that this point right here, we can call this f of x, okay? And we can call this distance right here x, okay? And this point is just a shift from this point, okay? I think that's the main thing that we need to recognize here. So let's say this is a shift by some constant h, okay? So we can say that this is h, but that means this would mean that this point is a distance of x plus h, okay? And so if this is a distance x plus h away from the origin, we can say that this vertical distance right here is just f of x plus h, right? F of x plus h. And so now we can say that our slope is just equal to, hold up, we can just say that's equal to f of x plus h minus f of x all over x plus h minus x, right? And these x's will just cancel out, and so that gives us the slope is just equal to f of x plus h minus f of x over h, okay? And so what we say the derivative is, that is the slope at a point, okay? So what we can do to find a derivative is if we move this f of x plus h point as close to f of x, we infinitely make it close to f of x, essentially forming a point. So we can, before I move on, I just want to explain what a limit is. So a limit is when a variable, say we'll use x in this, approaches some value, let's say 0. And so let's say we have this function x squared plus x plus 3. Whoops. that is just equal to 0 squared plus 0 plus 3 is just equal to 3. Okay? This is essentially what a limit is just when a variable approaches some value. Okay? And so, what we can say that a derivative is the limit, right? The limit as h approaches 0 of f of x plus h minus f of x over h, right? Because this essentially tells us that this point is approaching this point as h approaches 0, right? Because f of x plus 0 is just equal to f of x, right? And so this definition right here, this is what we call the derivative, okay? This is the derivative, okay? So let's look at some examples with this. So let me just rewrite the definition right here. This x plus h minus f of x over h. Say we want to find the derivative of x squared. Well, this would just be the limit as h approaches 0 of x plus h squared minus x squared over h. And for this, we can just evaluate this by multiplying these, right? Sorry, I can't do this mentally. And we can just say that is equal to, oops, I always keep trying to write x. H approaches 0 of x squared plus 2x h plus h squared minus x squared. Oops, I shouldn't jump the gun and get so ahead. There. So these x's will cancel out and we get 2x plus h squared over h, and that is just equal to, and we can actually rewrite this as h 2x plus h, right, over h, and these will cancel. So now if we take the limit as h approaches 0 of 2x plus h, that is just equal to 2x. So we could just say the derivative of x squared is equal to 2x. Okay, so now there are many different rules to derivatives, okay? So first we have the power rule. Say we take the derivative of any x value to the nth power. We could just say that that is n times x to the n minus 1, right? And then we have the quotient rule, or I'll get to that later. We have the product rule, which says if we have some function of x times another function of g, that is equal to f prime. Oh, well, f prime is just notation for the derivative of a function. Let's write that up there. All right, right there. So we could say that is just f prime times g of x plus f of x times g prime of x. Okay? And then there's the quotient rule. So this one is a little bit of memorization, but I like to just, I don't know, it just comes to me naturally, but wait, I think it's just high low minus low high over low squared. So what that essentially means is just f prime of x times g of x, right? Minus f of x times g prime of x, right? Over g of x squared. Okay? So these are your basic ones, okay? But then we also have our trigonometric functions also we can take the derivative of. So I'm not gonna get too much into inverse functions because we're not gonna really need it for the MIT integral we're doing. But we have the derivative of sine of x, and that is just equal to cosine of x. Okay? Derivative of cosine of x is equal to negative sine of x. And then the derivative of tangent of x is secant squared. And then the derivative of secant of x is secant tangent. And then the derivative of cosecant, cosecant of x is equal to negative cosecant cosecant of x times the cotangent of x. The way I like to remember is anything with the will be negative, okay? And it'll be the cosine or the co-version of its opposite. So like for cosine, sine, cosine. But I think it works better with this. See how this is secant tangent? Take the cosecant, negative. Remember, all our cos are negative, times the cosecant times the cotangent. I'm not gonna get, like I said, I'm not gonna get into the inverse stuff because that we don't really need that. Okay. So now we know these. Okay. So now that we've done a quick review on what a derivative is, it's time we tackle this thing. Whew. What is an integral? Well, an integral, that is just the area under the curve. Let me see if I can draw a good curve. So say we have some point A and we want to integrate from the origin. We put our bounds at the bottom, at the top. So our lower bound is 0 and our upper bound is A. Okay? And essentially, wait, hold on, let me label this as f of x. Essentially, this is just the area under a curve. So we can say that this is equal to the integral of f of x dx. But before we even get to talking about it, let's see how do we derive this. So there's something we call Riemann sums, okay? And what Riemann sums are is they are these small rectangles that we use to approximate the area of the curve, okay? And so with these Riemann sums, as we approach an infinite amount of rectangles, we get to what our integral is, but that doesn't explain where the dx comes from. What is a dx? Well, let's say so going back to what we learned and in what do you call it, with the derivatives, we know that this y value right here is f of x, okay? And we know that the formula of a rectangle is just length times height. So we know that we can call this delta x, okay? This is also a delta x, okay? This would also be a delta x. This height would also be f of x, if that makes sense. And we go on and on and on with each rectangle, okay? So we say that any vertical value that will lie on this function is f of x, okay? And then it'll also have a width of delta x, okay? And so as we get infinitely small rectangles and we approach this area under a curve, we say that this delta x, as it becomes infinitely small, we call it d of x. So this indicates infinitely small delta x's. And so we established that any vertical distance that lies on this curve is f of x, okay? And so now what we can say is we can say that this is just the integral of f of x times dx, because all we're doing now is we are just summing all of our infinitely small rectangles, hence why this integral sign is a massive S, right? And then this is just the formula of a rectangle, right? Our f of x times our d of x. So basically, a quick review, this is just our sum, right? Sum of infinitely small rectangles, the area of infinitely small rectangles. Hold up. Area of infinitely small rectangles. Okay? And when we want to integrate from, say, one point right here to a point right here, we and say that this is some random point A, or distance A from the origin, and then this is some distance B from the origin. We can say that this is just the integral from A to B of f of x dx. And so now you may be thinking, what how does this relate to derivatives? Well, I'm not going to show you the proof because I'm not sure we have enough time to show the proof. But essentially, if we take the integral of the derivative of our function f of x, right? So f prime of x, that is just equal to f of x. So essentially what this means is this is the opposite operator of the derivative. So that's, yeah, basically that's what essentially means. But this will, knowing the derivative of a function will help us with some specific integration techniques, but we'll get to that soon. So now that we have learned what an integral is, okay? Or conceptually, we have learned what an integral is. We have learned that it is infinitely small rectangles summed up to form the area of a curve. So now, how do we integrate? Well, since we know that the integral is the anti-operator of the derivative, essentially we want to form something that when we take the derivative of, it will give us our original function, right? So let's start with our power rule, okay? So when we take the integral of, say, x, this is the integral of x to the first dx. I don't want to make that look like a prime, so what we do essentially is we add 1 to the power and then we divide it by the power. So essentially this is for any integral of x to the n dx, we say that it is equal to x to the n plus 1 over n plus 1. And why does this work? Well, let's use x squared over 2 as an example. Let's take the derivative of x squared over 2. Well, we know the power rule is we bring over this and subtract it by 1. So we have 2x over 2. Our 2's cancel and we get x. And I'll just show a quick example with the n plus 1 too, right? X to the n plus 1 over n plus 1. We bring over this, subtract it by 1, and that just gives us n plus 1 times x to the n over n plus 1. These cancel out, and we get x to the n. Okay, that is essentially what our power rule is. Okay? And now, let's see how this works with power such as 1 over x squared. Well, this is just equal to x to the negative 2, right? Almost forgot the integral. So essentially what we do is we bring this over and add 1. Negative 2 times x to the negative 1. So that's just equal to negative 2 over x plus c. Why do we add the c? Oh my gosh, did I forget to add the c? Wait, in the last problem. I am so sorry I forgot to add a c. I'm so stupid. Oh, please do not crucify me in the comments for that. Oh my gosh. But why do we add the c? Well, say if we were to take the derivative of this constant, that is just equal to 0, right? Because let's graph this. Say this is y equals c. This has no slope. Any point on this line has no slope. Okay? So we say that the derivative of any constant is equal to 0. So we add the c is because we don't know if there's a constant present in this function or not. Because if we were to take the derivative of it, this constant would go away. So that is why we add the plus c. Okay? So let's take this for example. 1 over x. How would we do this? Huh? Because if we try using the power rule, right? We try using the power rule, right? Plus 1, that just, things just get confusing, right? Plus 1, negative 1. We get negative 1, right? Because these cancel out. This becomes negative. That's not how an integral works. So, we say the integral of 1 over x is equal to the natural log of the absolute value of x. And I'll just show you the derivative of the natural log. The derivative of the natural log of x, right? The derivative of the natural log is 1 over x, right? And the derivative of e to the x will always be e to the x, okay? So, knowing this, we say that the integral of 1 over x dx is equal to the absolute value, the natural log of the absolute value of x. Well, why do we say that? Well, say if we have some bound that is negative, right? Say we want to integrate 1 over x from negative 1 to 1, right? 1 over x dx, right? That would just give us natural log of x evaluated at negative 1 and 1, right? But say this was the natural log of x, not the absolute value. Well, this would just be the natural value of 1 minus the natural value of negative 1. But this doesn't exist. So this is why we have to take the absolute value. So when we take definite integrals and we have a negative bound, we can evaluate it. And then we just need to know how to integrate our trigonometric functions. Sine of x, that'll just equal negative cosine of x. That makes sense, right? Because the derivative of cosine is negative sine. So we just have to add that negative, so these will cancel out, right? Derivative of cosine of x. I mean, the integral is just sine of x. Oh my gosh. Can't forget the c. Sine of x plus c, right? That's obvious, right? The derivative of sine of x is just cosine of x. The integral of secant squared of x dx is just equal to tan of x, and you get the gist, right? It'll just equal, you see this pattern right here, the derivative of the answer will just equal to whatever is in here. And I'll just do the last one that we really need to know. Secant x tan x dx is equal to secant x plus c. Right. So how do we even work out with bounds? What does this mean? What do our bounds mean? Okay. So I'm going to go back to our example with 1 over x, right? Dx. That is just equal to our absolute value of x, right? Well, these bounds mean to evaluate it at a and b. So what that essentially means is we're taking the natural log of b and then subtracting it from the natural log of a. Like that. And when we have bounds, we don't add that plus c because we know that this function is being evaluated at different values, and we only add that plus c for because it's ambiguous, but these bounds suggest that this is the function. Okay. So it's time to learn some techniques to integrate, okay? So we are going to learn what is of something that is called U substitution. U substitution. What is it? What is essentially U substitution? Well, it's taking more complex values of x and then subbing it to a different value, and usually is u, and then using that to solve an integral. But it is a little more complicated than just straight up subbing it in. We have to have, just like we have a dx was our infinitely small x component of our rectangles. We need to turn this into a du, which would be an infinitely small u width of our new rectangles that we make by substituting our complex value of x into u, okay? Into our u rectangles. So let's take an example. The integral of x. Wait, let me think. Integral of x times the square root of x squared plus 1 dx. So let's do. I'll show you a quick rundown. So basically, we see this complex value right here, and we see that something that closely resembles its derivative is right here. So we can say is we can set our u equal to x squared plus 1, right? And then we could set our du equal to 2x dx. And if we divide our 2 on each side, we get that 1/2 du is equal to x dx. And recognize that we have this x right here and this dx. So essentially what this is this is just 1/2 times the integral of the square root of u du. Okay? And now we can easily evaluate this. This is just 1/2 times the integral of u to the 1/2 du. Add 1, and we get this is just 1/2 times 2u to the 3/2 over 3 plus c. But we can't forget that we have to substitute back in our x value, or our x value. So what this actually is this is equal to 1/2 times 2 times x squared plus 1 times 3 over 2 over 3 plus c. Essentially the answer. Well, these twos will cancel out, and but that is essentially how a u sub works. Okay? Let's do another example. The integral of tan of x. We know that tan of x is equal to sine of x over cosine of x, right? So what we can do is we can rewrite this as the integral of sine of x over cosine of x, right? dx. And so what we can do now is we can set this cosine of x equal to u, right? And then we can say that du is equal to negative sine of x, right? dx. Bring that negative to the other side, and we get that negative du is equal to sine of x dx. So now we can rewrite this as the integral of u du. And this just evaluates to negative u squared over 2 plus c, which is equal to negative cosine of x squared over 2 plus c. Alright, so now what do we do if we have a definite integral, say from 1 to 4 of our original integral x over x squared plus 1? Well, like we did in the earlier example, set u equal to x squared plus 1, du equals 2x dx, 1 over 2 du equals x dx. So 1/2. Well then, what do we say our bounds are, huh? What should we say our bounds are? So what we do is we plug in our bounds right here, and we plug it into the substitution we made. So when x is equal to 1, we see that u is equal to 2. And when x is equal to 4, we see that u is equal to 17. So when we take the integral, we get that this is equal to 2 over 3 times u to the 3 halves, evaluated at 2 and 17. I'm honestly not gonna do the whole like I'm not gonna evaluate it. Like if you really want to evaluate, you could evaluate. But essentially, this is the basics of how to evaluate something like this. Okay, so now before we can get on to doing this MIT integral, we need to learn how to do partial fractions. Okay? So let's essentially the whole basis of partial fractions is splitting up a fraction into two separate fractions where we have a of x plus b of y, right? To which we can separate and then split up into each groups, then to solve a system of equations to find certain values and then integrate an easier function. So it's kind of hard to show just without actually showing you how to do an integral using it. So I think I'm just going to show you an example, a very easy, quick example. So basically, let's say we want to take the integral of 1. Let me make that a little bit cleaner. 1 over x plus 2 times x plus 1. So essentially what we want to do is, since we have two separate portions in our denominator, we want to have two variables that we want to set up like this. And essentially what we're doing here is we are going to solve for values of a and b such that when we add them, we get this right here. Okay? And the rule with partial fractions is you want your numerator to be the degree 1 degree less than x. So say if our numerator was x squared plus 1, our denominator, our numerator would be ax plus b, and so on, so on, so forth. Okay. So essentially what we want to do is we want to get rid of these denominators, okay? Or actually we want to make common bases, right? In our denominators, and we want to add them together, okay? So what we're going to do is we're going to multiply x plus 1 with a and x plus 2 with b. And so when we do that, we get ax plus a plus bx plus 2b over x plus 2 multiplied by x plus 1. And so now what we can do is we can group our x's and our constants together, and we can see that we have a plus a plus b with this x on the outside, right? Plus another parenthesis a plus 2b. Do you guys see the resemblance of what we're trying to do? I'll give you a hint. We are going to make a system of equations. So now to make this system of equations, we recognize that a plus b is a part of our x constant, right? And we have no x constant. So that means this is simply equal to 0. Say if this was like plus 2x, then this would be equal to 2. That makes sense, right? Because essentially what this is essentially our integral, but split into two separate sections now. And we see that there is no x portion in the numerator, so this is just 0. So we can say a plus b is equal to 0, right? And then we see that this has no x attached to it, so this must be our constant. And our constant is 1 that is in the numerator. So we say that a plus 2b is equal to 1. And now we just solve the system of equations, multiply this by -1. These a's will cancel out, and we get negative b is equal to -1. It's canceling, and we get b is equal to 1. And if b equals 1, a equals -1. Right? That makes sense. And now going back to this. Remember when we said we split our integral into two separate portions like this? Now we can just integrate this, and we know values of a and b to which we can substitute into this and integrate. So now we can just say that this is the integral of -1 over x plus 2 plus 1 over x plus 1 dx. And a cool thing about integrals is we can separate this into two different integrals. We can say that this is the integral of -1 over x plus 2 plus the integral of 1 x plus 1. This is an easy substitution, but when you do the substitution, you'll figure out that this is equal to the natural log of x plus 2 plus the natural log of x plus 1 plus c. Oops. This is essentially our answer. So essentially, I think we have the knowledge needed to tackle our MIT integral as a whole. So, all right, so we have made it. We have made it to the MIT integral. So now you may be thinking, where the hell do we even start? So I think we should start this integral by rewriting it as sine of x, right? Over cosine of x over 2 plus rad 4 plus cosine of x dx. And I think you should be able to spot that there is an obvious u substitution here. And that is setting u equal to cosine of x. And then du is equal to negative sine of x dx, which means negative du is equal to sine of x dx. Okay, so I'm going to put this substitution over here, and I'm going to now show you what this should transform into. This should now transform into the integral of 1 over u, right? The integral of 1 over u times the square root of 2 plus the square root of 4 plus u. Perfect. Oh, du. Can't forget our du. Right. So let's just erase this all and rewrite our integral, leaving the substitution up there. Okay, so we had the negative integral, right? No, not, yeah, right. The negative integral of 1 over u times radical 2 plus radical 4. Oops, can't draw my radicals. And now we're going to do a substitution exactly like we did in our last u sub example. So we're going to let w equal to rad 4 plus w, right? And we're going to do w squared is equal to 4 plus u. W squared is equal to, w squared minus 4 is equal to u. Du is equal to 2w dw. Okay. So we know that, right? So we know that we can do this. We can now make this substitution. Negative integral of 2w, right? Over w squared minus 4 times the integral of 2 plus w dw. It's getting a lot more easier to write. Gonna write this substitution up top. Okay, there. And this is what we get. So let's just rewrite this now. And we could take the 2 out. So we can just rewrite this as negative 2 times the integral of w over w squared minus 4 times rad 2 dw, right? And so now, just to make this next substitution easier, what we're going to do is we're going to rewrite this as w over, notice that this is the difference of two squares. So we're going to write w minus 2, w plus 2, times the integral of 2 plus w dw. And so now we're going to redo this one more time with our radical, and we're going to say z is equal to rad 2 plus w, right? Z squared is equal to 2 plus w, right? Z squared minus 2 is equal to w. 2z dz is equal to dw. Let's add that substitution right up here. Oops. So now, essentially, we want to rewrite our integral. Okay, so this is just negative 4 times the integral of w, which you know is z squared minus 2. And now, what about these? Well, essentially, what we can do is we can just manipulate this right here to look like this. So we can subtract 2 on both sides. So we can do w minus 2. And then we can do z squared minus 2 to get that w minus 2 is just equal to z squared minus 4. So we can say this is z squared minus 4. And now we can do the same thing with w plus 2. And we'll realize that these 2's will cancel out. And that'll give us w plus 2 is equal to z, right? So we're multiplying by z, right? And then we are... Oh, my bad. Z squared, sorry. This should be a squared, right? So this is... Whoops, can't draw for my life. Z squared, right? And we are going to multiply in our numerator. This is now z, so this is just going to be multiplied by z. And then we're going to multiply the z that we got from this right here. So multiplied by another z, dz. And we should recognize that dz should cancel out with that. And that should give us negative 4 times the integral of z squared minus 2 over z squared minus 4 dz. Okay, so let's rewrite that. Let's erase all of this. Let's make this easier for us. Okay. We have the integral of z squared minus 2 over z squared minus 4 dz. So now what we can do is we can divide these, okay, to get something that will make it that will be easier to integrate. So let's do that. So we're going to divide z squared, right, minus 2. Z squared goes right here. Gives us a 1 up here. Negative 2, right? And to get to 4, we're just going to have to add another negative 2, which gives us our remainder. Or, my bad, I forgot. I haven't done box multiplication in so long. Whoopsies. This should actually be... Hold up, sorry. This should be... Sorry, it should be denominator, not numerator. I can do this, but I can't divide. Minus 4, right? We start with z squared right here. 1 minus 4, right? and then we add 2, and that is our remainder. So now our new integral is 1 plus 2 over z squared minus 4 dz. Let's rewrite that. The integral of 1 plus 2 over, z squared minus 4 dz. Recognize how this is the differences of two squares? Well, good thing you did, because guess what? This is a fun partial fractions. Let's split this up into two integrals to make this easy. And let's take out this 2 once we split it up. Okay. And well, this should just evaluate to z. So we just have z plus 2 times the integral of 1 x plus 1. Oh, my bad. Shouldn't be x. Should be z. Sorry. Z plus 1. Z plus 2. dz. Okay? Now all we have to do, we are so close. All we have to do is integrate this. So let's get this whole mess out of the way, and let's rewrite our integral. Oops, should be easy. So close. We are at the end game. Let's see. Believe I'm missing. Oh yeah, right. I'm sorry. I just went back and I just remembered that I'm forgetting the minus 4. So let's add this minus 4. There should be this should be minus 8 right here. You see with MIT integrals, it's very easy to get tricked up. So actually, we should have negative 4 minus 8 times this integral. I almost forgot about this, but then it just popped up in my head that something just didn't look right, and then I realized I forgot that in my numerator. So let's just rewrite this integral now and then we can just go on with integrating this. Okay. So we have negative 4z, right? Minus 8 times the integral of 1 over z plus 2 times z minus 2, right? dz. And now remember what we said about our partial fractions, right? Z plus 2 plus b over z minus 2, right? So we have az. We essentially end up getting az. Oh my gosh. Cannot tell these apart. This is a 2. This is a 2. Well, let me erase that and just make that a visible 2 so it doesn't trip up viewers. 2. There we go. Actually, nah, I can make that one better. There, 2. So we have az minus 2a, right, plus bz plus 2b. And then just like if we do the grouping, just like we did when in the example problem, we get a plus bz plus negative 2a plus 2b Right. And now we can set up our system, which I'll do over here. A plus b equals 0. And then minus 2a plus 2b equals 1. I'll just multiply this by 2. These a's will simply cancel out. And we get 4b is equal to 1. And we get b is equal to 1/4. And then that gives us a plus 1/4 equals 0. That gives us a equals negative 1/4. So now we rewrite this as negative 4z minus 8 times the integral of negative 1/4 times 1/z plus 2, right? Minus another 8 times the integral of 1/4 times 1/z minus 2 dz. Oh my gosh, I forgot my dz on my first integral. What am I doing? Hold up. Give me a second. Just rewrite this. Should be 1/z plus 2. Oh my gosh, I have no space. dz minus 8. And when we evaluate this, we can take out the 1/4, right? So we can get minus, or no, this would be plus the 8/4. This gives us 2 times the integral of 1/z plus 2 dz minus 2 times the integral of z minus 2 dz. And these are two easy substitutions. And so we get 4z plus 2 natural log of the absolute of z plus 2, right? Minus 2 times the natural log of z minus 2 plus c. And now let's get a drum roll. Let's get a drum roll for our final answer. When we make all of our substitutions that we have up here, we get the answer to be, guys. The answer to be negative 4 squared times the square root of 2 plus the square root of 4 plus cosine of x. Right, minus 2 plus 2 times the natural log of square root of 2 plus 4 times cosine of x. Oh, my bad. Not cosine, sorry. Times the square root of 4 plus cosine of x plus 2 minus 2 times the natural log of the absolute value of 2 plus the square root of 4 plus cosine of x minus 2 plus c. And when we simplify this, we get our final answer. Our final answer to be -4 times the square root of 2 plus the square root of 4 plus cosine of x plus 2 times the natural log of the square root of 2 plus the square root of 4 plus the cosine of x plus 2 over. Actually, let me write that a little bit more cleaner. Looks a little sloppy. The square root of 4 plus. Oh, my bad. It should be the square root of 2. Oops. Times the square root of 2 plus the square root of 4 plus cosine of x plus 2 plus 2. Let me make this absolute value a little bit larger. Oh, I have shaky hands, I'm sorry. All over the square root of 2 plus 4 plus cosine of x. Well, let me rewrite that s. Cosine of x minus 2 plus c. And that, ladies and gentlemen, is our answer to this MIT finals problem. Whew. Well, that was a long journey. We basically started from what people learn at the beginning of calculus, the basics of calculus, the derivative, what everybody knows. It is the basics. All the way to a problem that some people look at, scratch their heads, and go like, what the heck is this? And walk away. We have worked our way up, and I'm so happy that we were able to figure out how to do this MIT integral. I hope you guys enjoyed this video, and I hope you guys want more content about this, about stuff like this. And that is all I have to say. Goodbye.